line, and from that you can deduce why the travel speeds are so low. What we found, here's an example, that if you take the really slow travel speeds, 0.23 metres per second, what we found is this person travelled through high densities, E and F, for 77% of their journey. So wherever you see a very very low travel speed, it's because high densities. And that's not surprising. That's beginning to suggest that all of our data seen from the past that engineers have been using makes sense. The reason that these guys are travelling slow is because high density, not because they were obese, although we can't rule that out. But this is not pointing to the fact that they were obese and so they were travelling slow. In fact, when you look at the average travel speeds that we calculated for the 3 stairs, they're much higher than what the 2 earlier studies, the NIST study and the VLAG study, were suggesting. In fact, we were about 45% larger than the NIST study. And also, the low travel speeds were incurred by people who were travelling at least 60% of their journey through levels of E and F, level of service on the stairs. So we begin to understand why the speeds are so low. And then we also we break down the travel speeds into the normal body mass index, overweight, obese, and morbidly obese. And the travel speeds, average travel speeds for these people are the same. So what this is showing us is that there's no correlation between body mass index and fitness with these travel speeds. Again, I must emphasise that the results may be masked because of the high degree of stoppages on the stairs. I want to move on to response times. We determined response times from 119 occupants in the World Trade Center. Now, what we did was, in the original study, we had very coarse bands to place the response times in. They were not very useful to us for doing engineering analysis. So we went through, the Greenwich team went through, and we refined the bands and redid all the analysis, and we came up with finer graduations to give us useful data for response time analysis. If you compress these bands, and these are the time bands you see up here, 0 to 1 minute, 1 to 4 minutes, 1 to 8 minutes, and so on, all the way up to 44 to 72 minutes. If you then compress these bands down to a region less than 1 minute, between 1 to 8 minutes and greater than 8 minutes, we find some interesting results when you stratify the building into low, mid and high, in these groups of 30 floors. What we find is that within each floor group, approximately at least three quarters of the population have moderate response times. And moderate response times here is between 1 and 8 minutes. So the engineering calculation where you put 0 to 2 minutes for this type of calculation for the World Trade Center is highly inaccurate. It's between 1 to 8 minutes is the bulk of the people responding. The high region also has the highest number of moderate responders, 1 to 8 minutes, and the lowest number of rapid and long responders. And we think that's because of the proximity to the impact floors. We think that the low rapid responders are due to the fact that occupants probably needed time to recover. They felt the impact greatest. They were shocked most perhaps, and so they needed the longest time, longer to react, so you don't have so many rapid responders. And also we don't have as many long responders because they know what's going on, they've experienced it, they've seen it, and they want to get out of there. So we have smaller numbers there. This is the response time distribution we've generated. I'm running out of time, so I'm going to be quicker. What you see here is the characteristic log normal curve that you see for a response time. So we're seeing characteristic log normal curve of response times coming out of the World Trade Center. Another interesting thing we looked at is the number of tasks people undertook during the response time phase. We measured 469 activities or tasks that people undertook, these 119 people, and we broke these down into 2 categories, what we call information-seeking tasks and action tasks. If you look at the information tasks, these involve people attempting to find out what's going on, grabbing information, seeking information. There were 175 of these information tasks undertaken. The 3 most common were sort information, sort environmental information about smoke, about is the staircase okay, and so on. information from colleagues was the next highest, 25% of the sample, and then waiting for further information. So that was an information task. I'm going to wait until somebody tells me what's going on, and only 9% of the study did that. Action tasks were tasks that people involved in physical actions prior to commencing the horizontal evacuation phase. We measured 294 action tasks. The three most common were collect items, 49%, instruct others to evacuate, 18%, and searching the office floors, 7%. Now, when we look at this data, we see that there is a positive correlation between the number of tasks completed and the response time. The more things people do, the longer they're going to take before they respond. Almost 1 in 10 participants do not complete any tasks prior to commencing horizontal evacuation. So about 10% of people actually did not complete a task before they started to evacuate. On average, a person completed 4 tasks prior to evacuating. Half the population completed 3 or less tasks, and 4 in 5 participants undertook 2 action tasks prior to evacuating, and 4 in 5 undertook 1 information task. If we now correlate the response time with the number of tasks people did, we find that information gathering tasks take about 60% longer than action tasks. So what this is telling us is that you can reduce the overall response time by giving people good information, solid information from an authoritative source will reduce the need for information gathering tasks. And that can have a substantial impact on the overall response time. The other thing is that action tasks also take quite a bit of time, and you can reduce the time required or even the frequency of action tasks by training people. Don't collect your briefcase, don't collect your phone, just get the heck out of there. And that's a training issue. Finally, what I want to mention is the issue of risk perception. And basically what we found was those who experienced were in the high risk categories in the response phase, because we measured the risk perception at different phases of the evacuation, but in the response phase, those who experienced high risk reacted 26% faster than those who had experienced low risk. I haven't got time to go to the conclusions of this, but I think I've got no time left. Okay. What I want to show you then, just briefly, because I think this is very important, especially for the next session. And what did I tell you, Carol, this is not working? One of the things that's, I think, very important, we looked at evacuation efficiency through computer modelling as a function of floor height and population density. What these results tend to show us is that for a given building configuration and population density, as the number of floors increases, the average floor evacuation efficiency decreases until a steady state condition is reached, where that graph begins to plateau out. It's a steady state. And that means, for that population density and that stair configuration, I can keep on adding as many floors as I want, and I'm not going to decrease the evacuation efficiency. But the other interesting thing is that if you now take one of these graphs and you start adding people, this curve begins to drop. And so it tells us for a given staircase design, there is a critical population density for which you cannot evacuate the building by stairs alone. And I think that's a key finding from this study. Thanks very much.
Okay, at this point, I'd like to ask the three presenters to take a seat up on the panel on the table over there. We're going to have